Hello everybody, my name is Chris Brady, author of the Boeing 737 Tech Guide and the Boeing 737 Tech Site. And this presentation is about the 737 alternate forward C of G option. So I'll start by doing a quick introduction into what this option's all about, then go into a little bit of theory, on then to series differences, particularly short and long-bodied aircraft differences. A look at how it's used in practice. Then the next two sections, choosing limit positions and OPT configurations, probably more pitched towards airline management and sort of fleet tech captains, but quite useful, I think, for you guys on the line to see the processes behind what you end up using on the line. And then finally some OPT examples and a word on FMC generated speeds. As always, please treat your company training and manuals as the authoritative source of information. Okay, so on to the introduction. This option, the alternate forward C of G option, has been around since 2000. In actual fact, the graphic I've got there is an AFM extract where the envelope was generated in late '99. It starts as an option for the 737NG. In fact, it was specifically for the BBJ, and it's now also available for the MAX family as well. Use of the option can give a takeoff and landing performance improvement whenever the takeoff weight is limited by either field length, brake energy weights, climb limits, or obstacles. And it does it by giving an increase in the RTOW, climb gradient, or a reduction in takeoff runway speeds or runway length. Now, worth mentioning that even if you're not performance limited, use of the alternate forward CG option can usually give reduction in takeoff thrust. That gives maintenance savings with engine life, or a lower takeoff flap setting, which gives fuel savings. So quite a useful option. Right, inevitably there's got to be a little bit of theory just to help you understand how this works. I will keep it short. Right, to explain the alternate forward CG option, you've first got to understand the effect of centre of gravity on lift. Lift acts through the centre of lift, CL, as shown there on the aft arrow. Weight acts through the centre of gravity, and C of G is always forward of CL. That's by law, and I'll explain why in the next slide. The lift and the weight, because of their distance apart, that they act as a couple, and that couple rotates the aircraft nose down. And the reason that it has to act this way round and not the other way around to pitch nose up is that it gives static pitch stability. So what we mean by that is, if the aircraft were to enter an upset which caused the nose to pitch up, the increase in alpha and hence lift will increase, which creates a restoring nose down pitch moment. So the whole thing is well, there you go, statically stable in pitch. It's self-correcting. Now, we clearly can't have the aircraft flying around, trying to pitch down all the time. So what we've got is the horizontal stabilizer that acts to create a downwards force, counteracting that lift weight couple. That keeps the aircraft in equilibrium. In other words, continues it in level flight or climb and descent as demanded by the pilot. So the horizontal stab counteracts that lift weight couple. Now, the horizontal stab, you can think of it as creating negative lift. It's creating lift in the downward direction. So to oppose that, the wing has got to create more lift to to oppose both the excuse me the weight of the aircraft and the negative lift of the horizontal stab. That total wing lift is what we know as the lift coefficient, CL, which is the thing that appears in all the formulas, but cast your mind back to ATPL days. Now the effect of forward CFG on lift is basically as follows. So the further forward the CFG, the greater that lift weight couple, because the distance between the two arms is greater. That means that the rotational force created by the couple is greater, so therefore there's got to be more negative stab lift required to counteract it. That means with that greater amount of negative lift off the stab, you've got to have more lift from the wings to keep the aircraft in level flight. That effectively shifts the lift curve down at all angles of attack on the standard lift alpha curve. Conversely, the further aft the CG is, then the lower or the lesser the lift weight couple, the lower the rotational force, less negative stab lift is required, and therefore the less wing lift is required. That is obviously beneficial. That shifts the lift curve up at all angles of attack. Just touching on the CG and the cruise, though it's not particularly applicable to this option, but just to complete the picture. In the cruise, the more forward CFG, a more forward CFG, it translates into more lift required, which is gained by more thrust and hence a greater fuel burn. And that's why most commercial operators always try and load an aircraft towards its aft CFG limit, even those without the alternate forward CFG option. So it's always more beneficial, generally, to a point, to load an aircraft with an aft CFG. Now for takeoff, a more forward CFG means more lift required to take off, and that basically translates to either a lower RTOW or more thrust required for a given takeoff weight, or a higher takeoff speeds, or a longer field length required for a given thrust weight. So generally, forward CFG has an adverse effect on takeoff performance. Now, normal takeoff performance data doesn't consider what the actual CFG position is. It always assumes that the CFG is always at the forward limit of the envelope, and that is the worst case scenario for performance. If performance could be calculated using the actual CFG, excuse me, say a mid CFG, then it would take account of the reduced lift required or reduced drag. The performance would show the aircraft could then lift a greater takeoff weight, have lower takeoff speeds, or reduced field length, or more assumed temperature thrust, whichever way you want to slice it. Again, a more aft CFG will give you better takeoff performance, but as I've already said in the previous slide, normal performance doesn't allow us to do that. Now, effective CFG on the climb. So for a given speed, the greater the lift required, the greater the angle of attack. That stands to reason. But the greater the angle of attack, the greater the drag. Therefore, if an aft CFG is used, less lift is required, the angle of attack will be lower, drag will be reduced, and that gives a better climb capability. Now, remembering that the climb performance is drag dependent. That might give a higher takeoff weight if your climb are obstacle limited. And I'm saying may because it actually won't always. The reason is that there's more to climb than drag, as I'm showing here. So for the climb case, drag is not the only factor. Because the takeoff speeds are lower when using an alternate forward CFG, you will get airborne earlier because your V-speeds are lower, but your climb gradient will be shallower because you've got less V2, less airspeed. And really, the way I think about it is that an alternate forward CFG takeoff is a bit like a negative improved climb. So with an improved climb, if you cast your minds back, what you're doing is where you've got a long runway, you're using that excess field length to stay on the ground longer. You rotate and take off later, but with faster V speeds. So when you do get airborne, you have a better climb gradient. Now, depending where the obstacle is, whether it's close in or further out, that may or may not improve your climb or obstacle limit. The way I've drawn it here, I've shown a close-in obstacle, which of course is adversely affected by improved climb, because with an improved climb you're effectively taking off closer toward the obstacle. With alternate forward CFG, you're using, as we've already seen, it enables you to use lower takeoff speeds. So your takeoff point is earlier, but when you climb out, you're climbing at a lower V2, which gives you a lower climb gradient. So I say it all depends, yeah, and really you've got to crunch the numbers on the day to see whether it'll work for you. Just the same as for an improved climb. Improved climb doesn't always work, just as alternate forward CFG doesn't always work for the obstacle or climb gradient situations. And finally, the effect of CFG on landing. It's very similar to the takeoff case. An aft CFG shifts the CFG curve upwards, thereby giving you more lift for a given alpha. That enables a lower VREF to be flown for a given angle of attack, which is particularly useful for long-bodied aircraft where VREF is limited by tail contact geometry, and I'll mention this again in a moment. A lower VREF will of course give you better stopping performance because you're touching down with a lower speed, but might impair the go-around climb performance for the same reason I've been explaining on the previous slide, that when you've got a lower speed, your climb gradient may be lower. Right, on to series differences. So, as I said, in 2000, Boeing first offered the alternate forward CG option on the 737. Initially, it was just for the BBJ and the 700 increased gross weight series, and they later rolled it out to all the others. Now, this option allows the operator to use one of two alternate forward CFGs. I've said usually 40 and 18%. If that was the case for the 700, and they're further after the forward certified limit to get the performance takeoff benefits that we've been speaking of in the previous slides. So what I've shown you there is the envelope for a 737-700. And you can see it, the first red dotted line is the red dotted line on the left is the standard forward takeoff and landing CG limit of 9%. That's the one you always have to use. That's the most limiting case. But there are two other dotted lines there, further back or further to the right, takeoff 1 and takeoff 2 for the alternate forward CG limits, which here are 14 and 18%. On the 800, a typical envelope might look like that. The values shown on this particular one, they're unusually close together at 15 and 17%. A more common choice of limits usually around the 22-26% range, give or take 2%. I will come on to choosing AFCG limits later in the presentation. I'll go into this in some depth with you. One thing to point out is that in this envelope, the alternate forward CFG limits are valid for both takeoff and landing. The previous one I showed you for the BBJ was actually just for use, or were only authorized for use on takeoff only. And this is the envelope for a MAX 8. Very similar to other Boeing models. It just looks different because on the MAX envelopes they're displayed with the CG axis lines fanned out, but they're the same. And this particular operator's got 15% and 21% limits, so they're a bit more normal than the previous 800 one that we were looking at. These are actually for takeoff only though. Okay, so I mentioned this before. Let's sort of cover this in a little more depth now. So there is a limit to the amount that the takeoff speeds can be reduced by using the alternate forward CFG option. Now, for long body aircraft, and by that I mean 8-900s or the 8-9-10 on the Maxes, the limiting factor is usually VMU, which is the velocity for minimums on stick. And this is to give the necessary aft body ground clearance. So that reduces the maximum allowable body attitude, and therefore alpha, and therefore VR on takeoff. Now, if VR can't be further reduced, then neither can the other takeoff speeds by regulation. And what I've done is I've reproduced up there in the top right of this slide the interrelationship between V1, VR, V liftoff, and V2, and you can see that they are basically all affected by each other. Now, the two which are particularly limiting for the long-bodied 737s are this V liftoff, which is a factor of VMU, both engine out 1.05 and all engine 1.1. And once VR is set by those, which it is because they're the limiting factors, then you're in certain cases your V1 and in pretty much all cases your V2 are also similarly limited. So so that's the limiting factor for your long-bodied aircraft is VMU, and that's purely because of the length of the fuselage. Now, for short-bodied 737s, your 6-7-7s, the aft body ground clearance is just not an issue. You really I've got to be working hard to try and tail strike one of these, and you won't do it even at low flap settings because the limiting factor for VR is usually the stall speed anyway. So the benefits of alternate forward CG performance are usually greater with short-bodied aircraft than long-bodied aircraft because they can maximise the full effect of the low VRs available from using the alternate CFG limit. Now, as we've seen, the aft CFG shifts the lift curve upwards at all angles of attack. That gives an increase in CL for a given alpha. For a given takeoff, the takeoff speeds, again specifically VR and V2, are based on the more limiting of VMU and VS, the unstick and the stall speed. So at aft CG, the field length benefit comes from a reduction in takeoff speed, because of your greater CL, required to produce a given amount of lift at a given angle of attack. That alpha can either be body attitude limited for your long bodies or stall limited for your short bodies. So that's kind of it in a nutshell. Why it's better for short-bodied aircraft than for long-bodied aircraft. I mean, long-bodied aircraft do still get a huge performance benefit, but not as much as the short ones. Okay, so let's have a look at this in practice. The takeoff performance data will use one of 3 forward CFG limits, and again, going back to this BBJ example, they are 9%, which is the normal forward takeoff limit. That's the standard envelope limit. That's, you know, with or without this option, that's always the most forward limit. Then forward takeoff 1, which in this particular case the operator is set at 14%, or forward takeoff 2, which this particular operator is set at 18%. Now, if your actual MACTO was less than 14%, then because the CG is not aft enough to exceed one of the 2 alternate limits, you've then got to use the normal forward limit of 9%. Your takeoff performance in that scenario would be no different to an identical aircraft without the AFCG option. If, though, after doing your weight and balance calculations, the actual MACTO was 16%, Then, because you're now after the 14% forward limit, you can use that first alternate forward takeoff limit, your takeoff one here, i.e. the 14% figures. And that will give you better takeoff performance over the standard 9%, albeit not quite as good as the 18% limit figures. And the final example in this case, obviously, if you're doing your weight and balance calculations, the actual Mach TOW is say 25%, or in fact anywhere between 18 and 33%, you can use the takeoff performance for the most aft alternate forward limit, takeoff 2, which here is 18%. And that will give a further improvement in takeoff performance over the takeoff 1 figures. Don't worry, I will put some numbers on these later on, and it'll all become more clear. Okay, I say this is now one of the two sections which is probably pitched towards more towards the airline management and tech captains, but I say it's good for you as line pilots to see and understand this, and I think that's probably why you're watching my series of videos, because they give you something a bit extra over the regular FCOM information. Okay, so choosing limit positions. The AFCG limit positions are not actually set by Boeing. When you order the option, you as the operator have to decide where you will put the limits. You choose them at the time of ordering the option, and then that's it. They're then set in stone. Note that you can choose 1 or 2 limits. The second limit's optional, but 99% of operators take it because basically it's the same cost to have 1 as it is to have 2. So if you already pay for it, you might as well use it. Now, once these CFG limits have been selected, they become hard limits in the AFM, and changing them requires a time-consuming and expensive AFM amendment and a corresponding change to the OPT. So really, it's best to choose the right limits for your operation first time. So what on earth might those right limits be? What you need to do is you need to gather your data. So to find the optimum alternate forward CG limit positions, the operator should do a statistical analysis of their loading data history to see where the takeoff CG clusters were, and then set the CG limits that include these clusters to get the maximum opportunity to use the option. Now, I've just roughly drawn something out here, so this is fictitious, but it's probably not untypical plot of takeoff CFGs where I've put a green dot on the envelope where each particular takeoff CG was. Now, an airline doing this analysis would use, I would hope, thousands, if not tens of thousands of data points. So what you get rather than dots, you kind of get a density cloud of where the distribution of takeoff CFGs are. Once you've got that, because data is key to this, then you can start to see where you will need to put the limits. I was saying, in my example, I've distributed them randomly, but on average they got an even spread across the full forward aft takeoff CFG range. Your airline may not have an even spread, and there will be reasons for that, which I'll touch on later. Now, the airline would now select 2 alternate forward CG limits that can be used by most of the data points. The first alternate forward limit shouldn't be too far forward, as it won't give enough performance gains to be useful for the sake of including too few flights. So for instance, if you want to include every flight, then you would need to have the first alternate CG up at around, I don't know, what's that, 7-8% or something. And 7-8% is just not enough of a performance gain over 6% to make it worth doing. So move it back, just grab the, I don't know, your choice, 90th percentile, to get, in this case, say 15% as your first alternate forward limit. Similarly, the second alternate forward limit shouldn't be too far aft, as that will exclude too many flights to be worth having. So again, you can roughly eyeball it with the limited amount of data here I've got here, but when you've got thousands of flights of data, it will be obvious where these limits need to be. Now, note that the further aft a CFG limit is set, as in this particular example where I've pushed it right back to 30%, yes, the better the potential performance gains for those flights that can use it. However, the further aft you set a limit, fewer flights will be able to use it. So here, I mean, only 2 flights can use that 30% limit, but those 2 flights will have enormous performance gains. Now, the drawback to that, apart from to those 2 flights, is that if the aft alternate forward CG limit, i.e. the 30% one in this example, is too far aft, then more flights with an aft CG limit will have to use the first forward AFCG limit, which reduces their potential performance benefits. So a balance has got to be struck. I mean, what I mean by that is any aircraft between, say, I don't know, 25 and 30% in this particular example will kind of be penalised, because they will only be able to use the performance benefits from 15%, whereas if we'd have made this limit 25%, anything with 25 or greater could have used the 25% limit. So it's it does require a little bit of thought as to where to set these limits. Now, this is a bit of an oddball, but I I have the example, so I thought I'd show it to you. Now, this is a real world example, so these aren't my made up limits, but the green dot data is my my stab at statistical takeoff CG plots. So this airline has chosen to have its alternate forward CG limits quite close together, and I say this is unusual, but it probably works for them. They excuse me, they must have had a reason for choosing these limits, and my guess is probably due to their loading policy and route structure. For instance, they may operate multi-sector legs where some passengers get on or off after the first leg, and some passengers stay on for 2 legs. So, kind of hub and spoke thing. In these circumstances, some airlines may load the point A to B passengers' baggage in the forward hold, and those passengers that are going all the way through A, B, C baggage in the aft hold, and that's just to make it easier for the ground handlers to load and unload the baggage. So you can say, right, well, when we get to the first stop, take all the bags out the forward hold out, leave the ones in the aft hold where they are. Whereas regular single leg operators can always load all of the baggage in the rear hold, or as much till it bulks out, and then just put the overflow in the forward hold to get the maximum CFG benefit. So that is probably what's going on with this airline. I mean, there could be other reasons as well, but it may be. I mean, it could be I don't know. Maybe they've got maybe their first class or business class compartments are quite well subscribed, or whatever it might be. Well, that's why you as an airline need to do your own data analysis to find out what works for you. Don't just assume that because everybody else uses, I don't know, 17 and 25%, then that will be what you need. Now, when the alternate forward CG option is approved, the authorized performance software serial number, the PSSN, you can see on that table on the right, for each aircraft in your fleet is shown in the AFM by serial number. Now, note that not all of the aircraft for a particular series in your fleet have to have the AFCG option. And you may ask why not, as crew, and the answer is cost. This option does have a fee, and it's about, I think it's $26,400 US dollars per tail, so that's per aircraft. For a new aircraft, I think the in-service one's probably a similar figure. So some operators elect to only have a limited number of aircraft with this AFCG option and deploy those aircraft on routes that would particularly benefit from it. I put them on the hot and high routes or airfields with short runways. A common combination for airlines which don't have the AFCG option on all the fleet is just to have it on, say, their SFP aircraft, because it complements SFP very well. You know, it gives a similar sort of benefit. Okay, OPT configuration. OPT, onboard performance tool, for those of you not yet using it, your OPT will need to be configured by your airline to include the AFCG limit data for all the aircraft in your fleet which have this option. And so the OPT administrator, which is what the screenshot is on the right, or a very small part of the OPT administrator, is used to configure all performance affecting items, such as which aircraft are SFP, which have got winglets, which might not have winglets, or which have got split scimitar winglets, engine thrust ratings for particular aircraft, brake categories, etc., etc., etc. So any performance affecting items that differentiate one aircraft from another are all defined per registration, per MSN in the OPT administrator. This particular example here is from an 800 SFP, which used the 15 and 17% alternate forward limits shown previously. Now, the user interface of the OPT can also be configured by your airline. And again, if you've only used OPT with one airline, you probably won't be aware of this. You probably think that all 737 OPTs look like this. Well, actually, they don't. They are pretty much infinitely configurable. And no two airlines' OPTs really look the same, surprisingly. But in this administrator, you can see how your airline chooses which airport and aircraft options are made available to the crew. Lots of obscure options, particularly available for the aircraft layout. Most of these are very rarely used. But if you've got the alternate forward CG option, then you will need to have the alternate forward CG position option selected in the OPT administrator, so the crew can select the necessary CFG. This screenshot shows how the forward CG position option looks in an OPT. Again, this is the BBJ example, which has got forward limits of 14% and 18%, and you can see I've just drawn in there green arrows showing to where they translate to on the envelope. Okay, so on to some OPT examples. The airfield I'm going to use for most of these is Santos Dumont Airport in Brazil. This has got the the very short runways of just over 1,300 meters. Makes it one of the most fill length limited runways in the world for the 737, and is in fact the airport that Boeing designed the SFP variant for. A look at the airport info tab, if you've got that available in your OPT, because again this is one of the things that is configurable, so not all of you may have that, but if your airline lets you have it, then you can see this sort of airport info, and that shows you the runway and the obstacle details, and there you go, balance field at 1323 meters. So for takeoff, you start by populating the airport conditions and the aircraft configuration, and then you select the AFCG limit that you'll be using from the drop-down list. So we got 6% tick there. If you click calculate before you enter the actual takeoff weight and zero fuel weight, then it will show you the limiting takeoff weight, or the RTOW regulated takeoff weight. Selecting a 6% AFCG limit, which is the normal envelope limit, that shows an RTOW of 60.7 tonne with flap 25. Just remember that figure. If you enter now the actual takeoff weight and zero fuel weight, that gives you takeoff speeds, and in this case, with natural takeoff weight of 57 tonne, a 26 kd rate with a small assumed temperature thrust reduction of 36 degrees is achievable. Now, if we then change the alternate forward CFG limit to 15%, because the weight and balance allow us to do that, that then shows an RTOW increase up to 61,314. That's an increase of 614 kilos over the 6% case. So you can see that this is significant. The improvement really is significant. Again, if you now bung in the actual takeoff weight, and again, to keep it simple, I'm going to use the same figures that we used in the previous example of 57 tonne. That shows a further derate down to 24k with no assumed temperature thrust reduction. That has reduced the takeoff M1 from 95.3 to 95.3 from 96.7 at 26k when using the 6% CG limit. So that has increased, or that will lead to a huge increase in engine life over the lifespan of using this this option, and engine life and reduced maintenance costs on the engines. Notice also, while we're on the page, that the V2 is 2 knots slower than the 6% case. Something we talked about in the theory section. If you select 17% alternate CG, that shows an RTOW of 61,453. That's a further increase of 139 kilos over the 15% limit, giving a total increase of 753 kilos over the 6% limit. So that's 3/4 of a tonne. And again, I take you back to what I said earlier about this second limit of 17% not being a particularly optimum one certainly for most airlines. If you were using an alternate forward CG of back towards 25%, then I would imagine you could see an RTOW increase best part of a tonne, if not more than a tonne, to be honest, depending on where you were going from. Again, using natural takeoff weight of 57 tonne in here. This is on the 17% case. You can see in this particular case, again, no further derate of assumed temperature destruction is possible, but the thrust is significantly reduced from the 6% case. So you're now down to 95.3 takeoff thrust. Okay, so let's look at an obstacle limit example now. So for that, we won't use Santos Dumont. We'll use Sao Paulo, which you can see here has got a stack of obstacles in the climb out path. Field length is not an issue. You got a takeoff distance there of 3.7 kilometers, so that should be enough. Using a standard forward CFG of 6%, you got an RTOW of 76,858 kilos. A check of the takeoff details shows that the obstacle limited weight is obstacle limit weight is the limiting case here. So all of the others, field, climb and tyre, are all less limiting than obstacle limited. If we use a 21% FCG limit, then the RTOW now increases to 77,165. That's an increase of 307 kilos over the 6% case, which I think we'll agree is quite significant. I mean, that's what, 3 passengers plus their bags. Check the takeoff details again, confirms that it's still obstacle limited. So that's just to sort of prove to you that there's no other limit has kicked in. I mean, I guess that the next nearest one would have been field limited, but it wasn't in this case. Taking a look now at landing dispatch case. So go back to Santos Dumont for this, for a field length limiting landing calculation. Now this is the case done at dispatch, so before you're airborne, because the rules are different, you recall. As with the takeoff case, you start by putting in the airport conditions and the aircraft config, then select the CAG limit from the drop-down list. You do that with 6%, gives you a regulated landing weight of 57,934 with flap 40. Move that up to 15%, and that gives it an ROW of 58,814. That's an increase of 880 kilos over the 6% case. That is a significant improvement. Take that up a little bit further to 17%, gives you 59,015, a further increase of 200 kilos over the 15% case, and a full ton over the 6% limit. Once you're airborne, as I say, the rules change. So en route, you start by populating the airport and aircraft conditions and aircraft config again, select CAG from the drop-down list, and using 6% with an actual landing weight of 59 tons, that gives a VAP of 134 and stopping distances between 1,007 and 1,261 meters. Going straight to a CAG of 17% with the same actual landing weight of 59 ton, that gives a VAP of 132, which has knocked 2 knots off the VAP than the 6% case, and reduced the stopping distance. Not a huge amount, but slightly, and they are all less than the 6% case, and that can mean that really can make the difference between getting into this airfield and not. One last case to look at, approach climb limit. So hot and high airfields, example I've used here is Bogota. The approach climb limit could be the limiting factor. You're up here at 8,360 feet airport elevation. Add in a bit of heat, and the pressure altitude will be higher than that. Can AFCG limit help us here? Probably, usually, not always, but often is I think the answer here. So let's look at this case. Using an OAT of 28 degrees, standard forward CAG limit of 6% gives an RLW of 67,436 with flap 30. And looking at the landing details page, you can see that indeed we are approach climb limited. Changing the forward CAG to 21%, that increases the ROW to 67,436. That's an increase of 256 kilos over the 6% case. So in this case, yes, changing the alternate forward CAG did help. And just a confirmation, going to landing details, again you see we are approach climb limited. Okay, one last thing to mention is the use of FMC Speeds. There is an AFM limitation that when operating at an alternate forward centre of gravity limited, you must disregard the FMC calculated takeoff or landing speeds if displayed, if you use the alternate takeoff, the alternate CAG for takeoff or landing. Now again, let me just stress, not all airlines have got this option activated for takeoff and landing. Some, in fact probably most, have only got it activated for takeoff. If it is, if your airline is one of those where you can only use alternate takeoff, alternate forward CAG for takeoff, then this is the page that the V speed you must ignore. And you get your V speeds from the OPT. If your aircraft has got the AFCG limit option for landing, and again don't assume that if it's got it for takeoff it has it for landing, but again your airline will tell you, then you must not use the speeds from the approach ref page. If you're using an alternate forward CAG limit, you've got to ascertain them from the OPT for the particular forward CAG limit that you're using. In this example, using flap 30 and a standard forward G of 6%, you can see that the VREF of 130 knots. Remember, VAP's VREF plus any additives, which we use standard 5 for wind. It's the same on the FMC and the OPT. That's because the FMC assumes that the aircraft doesn't have the AFCG option, or to put it, well, that's one way of putting it. The other way of putting it is that the FMC can't know, isn't programmed, hasn't got the capability or the functionality to know if your aircraft has got the AFCG limit option, and even if it did, you've no way of inputting that into the FMC at the moment. I mean, you never know, it may come in update 15. My feeling is probably not. The bottom line for you as crew is you can't use this if you're using an alternate forward CFG. So that's the case I've shown on the OPT there. For 6%, that's giving a VREF of 130. Sorry, a VAP of 135. If we change this to again, keeping all the other parameters the same, so we're still flap 30, but using an alternate forward CG of 17%, you can see it on the OPT that the VREF is reduced by 2 knots, as we would expect, to 128 knots. That's shown on there as a VAP of 133. But of course, the FMC speeds are the same, because the FMC doesn't know you're using the alternate forward CG. That corrected VAP must be flown to ensure that you achieve the landing performance given in the OPT. So, to summarise, takeoff and landing performance, and by that we mean increase in max takeoff weight, greater assumed temperature, lower V1 and VR, shorter field length requirements, better margins to VMBE, tyre limiting speeds, occasionally probably not likely on a 737, well theoretically possible, and sometimes greater climb capability. That can all be increased, by that I mean improved, by using the alternate forward takeoff CFG location instead of the conservative forward limit location specified by the standard AFM. The increase achieved by using the AFM alternate forward CFG performance option, which allows the operator to select one of 2 specified CFG locations. Using CFG locations after the forward limit decreases drag, actually improves your CL, lowers your stalling speeds, thereby increasing takeoff and landing performance. That's it in a nutshell. There you go. That's alternate forward CFG. As always, if you've enjoyed this video, please give it a like, subscribe to my channel if you haven't already done so, share it amongst your friends, and if you want to buy me a beer, then consider purchasing a copy of the 737 Tech Guide. It's available in paper format and electronic format for the iPad on the Apple Bookstore. Thanks very much for watching.